So let's look at an example where the population is not normally distributed and how we'll have to check the central limit theorem a little differently than we did in that last example. So we have restaurant bills at a given restaurant. They have this assumed population mean of 32.40, so that's our value for mu. We have a standard deviation of 8.16, so there's our value for sigma. And then they describe the population as heavily skewed to the left. So what that would mean in terms of a picture is if we had all of these restaurant bills, they would look something like this, which with a left skewed graph, we really don't have the means of calculating probabilities with that. We always want to have a bell-shaped curve. So our first question asks, explain why you cannot determine that a given bill will be at least $35. So if we had a bell-shaped curve, that's where we would go, draw our curve, and we know we'd be centered at 32.4, and then we'd have our cutoff of 35 and find the probability above, but we don't have that bell-shaped curve, so that all gets thrown out the window. So with this, it's not normally distributed, so we can't find the probabilities. So we can't find probability. So in our last example, where that first question got to ask about like a single glucose level, we could do that because our population was bell-shaped. Here we can't talk about what happens for an individual restaurant bill because it has a skewed distribution. But then what we can do is think about, what if we took averages? At what point could we start asking about questions about averaging a few different restaurant bills? So this next question asks, can you estimate the probability that the next 5 bills will average at least $35? So if we think about our central limit theorem, we could think about independence, and we should have independence here, like one bill to the next should be independent. And then randomization, we'll just go ahead and assume we have a nice random sample, but then our last conditions where we check sample size. And we have the sample size of 5, which is small, if we use that kind of cutoff of 30. And how we could bypass that before was our population was normally distributed, but we don't have that here. So if our sample's too small, we can't move forward. So our central limit theorem fails at the sample size condition. So can we estimate? Nope, because we failed the central limit theorem. That would mean if we collect these averages of 5 bills from this population, it's likely that our distribution of means will also be skewed to the left, and we'd be stuck in that same position as part A, where we can't find probabilities. So what if we use a larger sample size? What if we bump up to 50? Would all the conditions be met? Yes. Now we have the sample size of 50, which is larger than or equal to 30. So now when we take this, these means from the population, if we're collecting 50 of them, like we saw in that simulation, they become more bell-shaped because the values average out with these larger sample sizes. So what we can do now is define our model. So we need to know the center of the distribution and the spread of the distribution. The mean is the mean, so we just grab the population mean that we had, which was that 32.4. The standard deviation we need to adjust, so we take our population standard deviation and divide by the square root of our sample size, which is 50 now. And that should give us a 1.154. So with that, we can start to get an idea of the model for if we take 50 bills from this restaurant, what would the averages look like? So we expect an average of 32.4, and then we could get a number line going. If we're going a certain number of standard deviations above, I'm just going to go to 2 decimal places with these. So going standard deviations above, standard deviations below. So we can get an idea of our number line for having 50 bills and examining the averages. So this is showing our means, bell-shaped because we passed the central limit theorem, centered at 32.4, spread of 1.154. So now we can look at this probability of at least $35, but in terms of looking at a sample size. So here we go with a certain sample size. There's that word average that we want to look for in these questions. And here they're giving a cutoff of 35. So in terms of our picture, it's somewhere out here we have 35, and we want to have the probability of at least that much, so that'll be an area to the right-hand side. So first thing we need to do is get a z-score for our $35 value. So we'll take 35 minus the mean over our standard deviation, and that'll give us a z-score of 2.25. Then we'll go to our table to find this probability of having a z-score larger than or equal to 2.25. And we'll use the complement of, when we look up that z-score of 2.25, we should see an area of 0.9878. So after taking the complement, that'll leave us with an area of 0.0122. So that would mean there is a 1.22% chance the next 50 bills have an average of at least $35. So between the example in this video and the previous video, you want to pay attention to whether or not that population is normally distributed. If it is normally distributed, we can really get by on that sample size condition. But like with this example, with a skewed distribution, we really need to pay attention to that we're taking large enough samples. And they might not even say that it's heavily skewed. If they just don't describe the distribution of the population at all, we'll need to assume that it isn't perfectly bell-shaped. So then we'll want to always pass that sample size condition.